Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems, and in this module we will learn different aspects related to mass storage management. So, the learning objectives for this module are to understand different aspects of disk management like disk initialization, booting from disk, recovering from bad blocks, to learn how swap space is managed in disks, and to understand different RAID levels. So, we have been looking at different aspects related to file systems for the past few modules. So, a file system is the most visible part of the operating system, and it is divided into three major categories. One is the category where the users and the application programs interface with different operating system modules for the implementation of the file system, and then you have the data structures that have been used by the operating system, implemented in the operating system for the implementation of the file system, and then we have the disk where the files are actually being stored, and you also have a few other data structures that have been maintained in the disk. So, in this module we are learning different aspects related to the disk where the file system is actually stored. So, when you are looking at a new disk, it is just a platter of magnetic recording material, nothing is being written into it. So, this disk has to be formatted first, and that is called the low level formatting or the physical formatting. This low level formatting is usually done by the manufacturer, and what is done here is that the disk is divided into sectors, so that the disk controller can write into the sectors and read from the sectors. And when the disk is divided into sectors, a special data structure is assigned for each sector. The sector has got a header, a data area and a trailer, and the header has got a sector number that has been written into it, and the trailer has space for accommodating an error correcting code. So, whenever the controller is writing information into a sector, it will calculate this error correcting code from the bytes of data that is kept in the data part or the data region, and the ECC is written into the sector. And when it is read again, this ECC is calculated on the data region or the data part of that sector, and it is compared with the value that is already stored in the trailer. So, if both are the same, then it means that the sector is good or there is no corruption of data in the sector, but if it is different, if the stored value and if the calculated value are different, then the sector may be corrupted. So, if it is corrupted, then we can understand that we need to correct it. So, if there is only few bits of data in which corruption or has happened in the sector, then the data can be corrected using this error correcting code. But if there is error in many bits of data, then the error may not be corrected. And if an error is found, if the error can be found, then it reports a recoverable soft error. Suppose if the error cannot be cleared or it cannot be found, or if you do not really know which bit has gone wrong, then the sector is declared as a bad sector. So, many hard disks are generally low level formatted as a part of the manufacturing process, but the controller also can format the disk, can do low level formatting. So, if the controller is doing the low level formatting, then the user or the administrator can specify the block size for the particular disk. So, they can specify what should be the size of each sector. So, generally it can be 512 bytes or 256 bytes or 1024 bytes and so on. And in addition to this low level formatting, to use the disk actually or to hold the files or to put the file system into the disk, it is necessary for the operating system to record its own data structures on the disk. So, for this what is done is that the disk is first partitioned into one or more groups of cylinders, and each partition even can be treated as a separate disk. We have machines where there are multiple partitions, and we can even have a different operating system. Maybe you can have a Windows partition, we can have a Linux partition and so on. So, each partition can have a separate file system. So, this logical formatting or this creation of file system involves putting some file system related data structures into the disk. So, some initial data structures have to be put into the disk. So, these data structures may have may include information about the free space that is kept in the disk or the disk blocks that are free, the disk blocks that are currently being allocated, to which file is being allocated, and empty directory. All these can be initially put into this disk. And for a computer to start running, it needs an initial program to run, which is called the bootstrap program. So, the bootstrap program is responsible for initializing everything that is kept on the system. It will find the operating system is actually kept in the disk, and when the system boots up, this operating system will have to be brought into the main memory. So, the bootstrap program is responsible for finding the operating system in the disk and bringing the operating system from the disk into the main memory, and to move to a particular address in the operating system from where execution has to start. And this bootstrap program, the full bootstrap program, is also kept in the disk. It is generally kept in the block called the boot block, and this bootstrap program which is kept in the disk, in the boot block in the disk, has to be brought into the main memory. That is being done by a bootstrap loader, which is stored in a read only memory. The read only memory is not volatile. So, the contents of the bootstrap loader will remain intact even if the computer is shut down. So, the bootstrap loader brings into the main memory the full bootstrap program from the disk, and the full bootstrap program is stored in the boot block in the disk. So, if you have a disk which has got a boot partition, it is called a boot disk or a system disk. Now, we will see how bad blocks are managed in disks. Disks are prone to failure because of the moving parts. So, you see that you can know that the cylinder has to be rotated, you know that the heads have to be moved on appropriate cylinders and so on, and hence there is a possibility for disks to fail. So, if the disk failure is complete, if you cannot use the disk at all, then the disk has to be replaced and data has to be restored from the backup of the disk. But sometimes only some sectors become defective, and those sectors are called as bad blocks. So, if you have bad blocks, then manually you will have to handle this bad blocks. So, you need to find out which blocks are bad, and then you need to take necessary actions on that. So, how do you find which blocks are bad? One thing to do is that is to do a manual checking. You can run a scan on the disk and find out one sector after the other, go through one sector after the other, or go through one block after the other, and find out whether the sectors or the blocks are bad. And once you found that sectors are bad, what do you do with those sectors? So, you need to have some mechanisms for handling these bad blocks. There are two ways in which you do this handling. One is called sector sparing and the other is called sector slipping. So, in sector sparing, what is done is that the controller will maintain a list of bad blocks that are kept in the disk, and this list is initialized when the low level formatting is done in the manufacturing place, and it is updated over the life of the disk. And low level formatting, it will also set aside some spare sectors. Okay. So, when low level formatting is done, some sectors will be kept as free sectors or spare sectors, which will actually not be allocated for contents of files. Only when there is a bad block, this will be used. We will see how these spare sectors are being used. So, the controller will be told to replace each bad sector with one of the spare sectors. And in the case of sector slipping, what is done is that if one sector is found as defective, and say if 203 is the spare sector and 17 is the defective sector, then what is done is that you just move the contents of one sector to the another, keep moving the contents of one sector to the other, so that you will get a free sector. So, we will see how the sector sparing and sector slipping are different. See, in this figure A, we see that there are two spare sectors between the 0, sector number 0 and sector number 29, and there is a bad sector called 7. And for sector sparing, what is done, sector sparing or sector forwarding, what is done is that this spare sector is taken, the contents of sector number 7 is moved here and it is stored here. So, one of the spare sectors is used to store the contents of the bad block. But in sector slipping, what is done is that, so this is the spare sector. So, 29, it is close to 29. So, 29 is moved to the spare sector, 28 is moved to the place where 29 was present, etc., and so on, and you make space here near the bad sector and store the contents of 7 there. So, by this way you can manage bad blocks or bad sectors present in the disk. Now, we will move on to the next topic called the swap space management. What is swap space? The virtual memory uses disk space as an extension of main memory. Say we know that the main memory size can be small, and hence if there is no enough space to accommodate processes in the main memory, say partially executed processes can be swapped to the secondary storage device or can be swapped to the disk. They can be moved back and forth between the main memory and the secondary storage device. And this swap space can be kept as a file as a part of the normal file system, or it can be kept in a separate disk partition. So, even when the system is formatted or when the system is when the disk is partitioned, the space is allocated for swap space. So, it will be kept as a separate partition. But some operating systems, they allow the use of both types of swap spaces. The swap space can either be a file as a part of the file system, or it can be a dedicated swap partition, as in the case of Linux. Suppose if the swap space is a large file within the file system, then the normal file system routines are used to create the data related to the swap space, to name it and allocate the space. And you may have to navigate the directory structure, and you may have to go through the disk allocation data structures, but all these can take some amount of time. So, because it is a part of the file system, it is looking like a regular file. You do not have a specified allocated space for the swap space. It is very similar to how you access a regular file. So, because this takes time, you can improve the speed or improve the performance by which you access by caching the disk blocks in the main memory, and also by allocating physically contiguous blocks. So, if you allocate contiguous blocks for the swap space, when you are looking at swap space as a file in the file system, if you allocate contiguous blocks, then accessing the blocks one after the other will take less time compared to the other kinds of allocation methods. And when you have the swap space as a separate raw partition, this will be created, as I told you, during disk partitioning, and there is no file system or directory structure that is being kept here. But there is an entity called a swap space manager, which will allocate blocks and deallocate blocks from the raw partition. So, this will be a separate process that is running in the system continuously, which is called the swapper or the swap space manager or the swapper daemon and so on. So, this is responsible for allocating blocks and deallocating blocks from the raw partition. And the swap space manager will use algorithms which are optimized for speed rather than for storage efficiency. But the problem here is that it is possible to have internal fragmentation, because you have a big partition, swap space partition, you will be putting process into the partition, you will be taking out process from the partition here and there, and in due course of time it is possible to have free spaces here and there within this full big swap space partition. So, how do you avoid this internal fragmentation? But the internal fragmentation remains only till the system is booted up the next time. So, when the system is booted up the next time, there will be no information kept in the swap space, all will be free, all disk blocks will be free. So, this happens, or this is carried on, like our internal fragmentation will be there only till the system is boot up the next time. And we will see how this swap space management is done in different operating systems. In the traditional Unix kernel used swapping, but those days the Unix kernel was responsible for swapping entire process between the disk and the memory. So, process as a whole, they were swapped between the disk and the memory. But now you do not have a process being looked at as a full being brought into the main memory for execution, but we have other paging and segmentation mechanisms. So, they try to combine the swapping with paging. So, since demand paging is being done, the whole process is not brought into the main memory, only the required pages are brought into the memory, and these pages may have to be swapped out, not the entire process. And in 4.3 BSD flavor of Unix, it allocates swap space when the process starts, and it holds a text which can hold a text segment and data segment. The swap space is responsible for holding the text and the data. And in this case, the kernel will use swap map to keep track of the usage of the swap space. We will see how it is being done here. So, here you have a separate swap map for keeping track of text segments that are kept in the swap space. So, here you see that this is the swap map, and the swap map has got entries or addresses of disk blocks which hold text data, text information or the text region of the process. So, here we see that initially the first 3 blocks correspond to the text region, and they are fixed blocks, say 512K has been allocated for the text, and then we have one last block where only 71 is being used. But in the case of data, the data can grow over time. So, what is done is that initially you have space of 16K that has been allocated for data, but if it grows, if you need more memory space for data, then what is done is that 32K is allocated. It is increment, or it is doubled, and you allocate 32K. And if you need even more space, then this space, the amount of the size of the space allocated is again doubled, and you get 64K, etc., and so on. So, the way in which a swap space is allocated for text and for data are different for this 4.3 BSD Unix. And because it is different, you have different swap maps that have been maintained for keeping track of text as well as data. And in Solaris 1 machine, what is done is that it will bring the text segment pages containing code from the file system and use it in the main memory. So, we all know that the executable file will be kept as a file in the file system. The executable file can have text, data, and other regions. So, the text region of the will be taken from the file that is kept in the file system and be brought into the memory. But if it is not needed, it does not move it back to the swap space, but it will read it again from the file system, because the text will only be a readable or read only part. There will be no changes being done to the text part of a process. You will not write into the text part of a process. What will change in a process is only the data region. So, this text need not be written to the swap space and brought back again. You just do not store it in the swap space, you just ignore it. If it has to be removed, just remove it from the main memory, that is it. The next time if you want the same text region, you bring it from the file system, the files that is kept in the file system. And this Solaris 1 will maintain a swap space only for data region, because data region will vary over time. So, if you need to move out a data region from the main memory to the secondary storage, it will be put to the swap space. So, this will maintain information in the swap space only for the heap, the stack, and uninitialized data of the process. And in Solaris 2, what is done is that swap space is allocated only when a page is forced out of physical memory, not when the virtual memory page is first created. So, when you are trying to bring in a process into the main memory or a page into the main memory for the first time, you do not create swap space. But if you really want to move that page into the secondary storage, only then you create allocate space in the swap space for this particular page. But because the reason here is that modern computers have got lot of RAM space or main memory space, and hence this paging out happens very less frequently. And we will see what happens in the case of Linux. In the case of Linux, swap space is allocated only for anonymous memory. Okay. Anonymous memory is like memory that are not backed by any file, as we saw the heap region and the stack region and uninitialized data. All these are called anonymous memory, and swap space is used only for those. And the swap area, as I told you earlier, in the case of Linux, can be kept either as a swap file or as a dedicated swap partition. So, each swap area has got a series of 4 KB page slots which can hold swap pages. So, here they are looking at the page size being 4 kilobytes. So, there will be slots of 4 KB, and whenever a page is swapped, it will be brought into this page slot. And there is a swap map which will keep track of which slots are occupied or which page slots are occupied. So, if the counter, and the swap map will maintain an array of integer counters which will be initialized to 0, which will be initialized to 0. So, if a particular page slot is available or it is free, not being used, then the corresponding entry in the swap map will be 0, and if it is allocated, then it will be incremented as 1. Suppose if more than one process is using that particular page, then the swap map will increment it according to the number of processes that are using that particular page slot. So, if the entry is 3 in the swap map, then it means that 3 processes are using that particular page which is kept in the swap space. Now, we move on to this topic, that is this RAID structure. We all know that disk drives are getting cheaper, and hence it is possible to attach many disks to a computer system, and multiple disk drives can provide reliability through redundancy. So, this redundant array of independent disks are used to address performance and reliability issues. We will see like how this reliability can be improved. Suppose you have n disks and one of the disk fails, then there is a higher chance that the single disk will fail. So, if only one copy of the data is stored, then disk failure will result in loss of data. So, the failure rate of one disk among n disks is much more compared to the failure rate of just having a single disk. So, how do you avoid this loss of data? You need to go for different solutions, and one such solution is redundancy. So, what is redundancy? You need to store the information multiple times, or you need to store this information, or you need to duplicate the information. The simplest approach is to duplicate every disk. So, if you have data in one disk, that data has to be duplicated and kept in another disk, and this is called mirroring. So, when you have two disks which have the same information, whenever you write into one disk, that has to be written to the other disk as well. So, every write has to be carried out on both the disks. So, the resultant is now you have a mirrored volume. You have one original data, you also have a mirrored volume. But here the data is lost only if the second disk fails before the first failed disk is replaced. Say the first disk fails and now the second disk can be used. So, you continue to use the second disk. So, it takes some time to make this first disk working again or to repair the first disk. So, before this first disk comes back after repair, if the second disk fails, then you have no access to the data. So, the mean time to fail for this entire volume, the original and the mirrored volume, is that the time it takes to fail for one disk plus the mean time to repair the disk that was failed. You can also improve the performance via parallelism. So, when you have disk mirroring and when you are trying to read from the disk, so you have two disks, you have data present in two disks. When you are trying to read data from the disk, rather than reading from just one disk, you send the read request to both the disks. So, now it is possible to read information from both the disks. So, you can increase the speed with which you can read the data. So, for this what is done is that they introduce something called data striping. In data striping, it can be done as a bit level striping or block level striping. In bit level striping, what is done is that, say you have one byte of data which has to be written to the disk. That data, the byte of data is split into multiple disks, and say you have 8 disks, say you can write one bit into each of the disks. So, when you are trying to access data, read the data, you can read each bit from each of the disks and then combine it together. Even writing, so the byte is divided into 8 bits. So, in parallel you can write all the bits into the disk. So, it will take time of writing a single bit. So, to write a block or 8 bits of data, it will take only the time taken will be only the time needed to write one bit into the disk, because you are writing all the 8 bits in parallel. Very similarly, reading also can be done. So, by this performance can be improved. And so, here every disk will participate in every access. So, you can also do block level striping. In block level striping, what is done is that blocks of file are striped across multiple disks. Say you have 4 disks. So, the first disk you can write the first block, and the second disk you write the second block, and the third disk you write the third block, and so on. So, here also you can, while reading and writing, you can improve the speed, and block level striping is the most common one. And we see that mirroring provides reliability, but is expensive because it maintains redundant information. Striking will provide high data rates, but it does not improve the reliability. So, many schemes were developed which will combine disk striping along with parity bits to improve the reliability and to improve the performance. So, these schemes are called different RAID levels. So, the first is RAID level 0. In this is often called as striping. So, in what is done here is that a file is broken into blocks of data, and the blocks are striped across different disks in the system. And there is no redundancy here, there is no error detection done in this RAID level 0. So, you look at this diagram, say you have a file's data where you have block 0, 1, 2, 3 and 4, and block 0 is written into disk 0, block 1 is written to disk 1, block 2 is written here, block 3 is written here, and block 4 is written to disk 0. So, you find that block striping is done, and the blocks are being kept in different disks. So, because of this you get performance improvement, because when you are trying to read say block 0 and block 1 from the file, then block 0 can be read from this disk and block 1 can be read from this disk in parallel, and hence performance is improved. In RAID level 1, what is done is that a complete file is stored on a single disk. Here they are looking at only redundancy. There will be another disk which will have an exact copy of the file. So, it provides complete redundancy. So, when you are trying to read from the disk, you can read in parallel, because you can read say one block from here and the second block from the second disk and so on. But while writing, the problem is that you will have to write into both the disks, because you are maintaining a redundant copy. So, each data has to be written twice. So, this is the most expensive RAID implementation, because it requires twice as much storage space. So, this can be seen in this diagram. So, here block 0 till block 4 is kept in this first disk as well as in the second disk. So, a redundant copy is maintained. There is no striping here, only redundancy is maintained. Now, next level in RAID level 2, it will stripe the data similar to level 0, but here instead of doing block level interleaving, here bit level interleaving is done. So, a bit striping is done here. And another thing is added here to improve the reliability of the data. What is done? You include an error correcting code. So, the error correcting code is also maintained in another disk. So, you have multiple disks to maintain the data, you have disks to maintain the error correcting information, and in addition to that you also have a disk which will store parity bits, so that you can use the parity bits to reconstruct the corrupted or lost data. So, the ECC can be used to find out or detect if there is an error, and the parity bit can be used to correct the data. So, here you see that you have block 0 being put in this disk as well as this disk in 2 disks. So, bit level interleaving is being done, and block 1 is also being put in the multiple disk and so on. In addition to that, you have disk for storing ECC as well as for parity. But the problem here with this level 2 is that the disk needed to detect which disk had an error. So, the modern disk actually can already determine if there is an error. I told you earlier that ECC codes can be added with the sector. So, what they did that they tried to avoid this ECC disk and had only a parity disk. So, if the sector is bad, then the disk itself can tell us. So, you use the parity disk alone to correct it. And problem with level 2 and level 3 is bit interleaving. So, to access a single file block of data, we must access all the disks. So, even for a single byte, single block you need to access all the disks. So, level 4 interleaves file blocks. So, it uses a single disk for parity. So, now the parity is calculated over data from multiple blocks. In the case of level 2 and 3, you can calculate it only over a single block. So, if an error is detected, you need to read the other blocks and other disks to reconstruct the data. So, here we can see the difference of level 4 compared to level 2 and level 3. So, in level 3, we see that A, B, C, D, A naught, B naught, C naught, D naught are kept in the same disk. Say for example, you have A1, A2, A3 and A4, or different bits of a block are kept in different disks. Okay. So, for the second block, say B, it is B0, B1, B2 etc., different bits of the same block are kept in same byte are kept in different disks. And when you are calculating the parity, what is done is that for block for byte A, which is kept in 4 different disks, you calculate the parity and store here, and for B, which is a single byte, you calculate the parity and store here. But in the case of L4, you are doing a block interleaving. So, one byte will be kept in only one disk, and the second byte will be kept in the second disk, etc., and so on. So, while you are calculating the parity, what is done is that you calculate the parity bit over the first bit of the first byte, the first bit of the second byte, first bit of the third byte, and the first bit of the fourth byte. So, all these are combined together to calculate the parity. So, while you need to check this particular block, you need to check all the disks to calculate the parity, and for each bit of each block, you need to check all the disks to calculate the parity. So, the reads are simple to understand. If you want to read block A, you can read from disk 0, but if there is an error, you need to read all the blocks and calculate the parity. And the next is RAID level 5. In this, it files striped data and checks the data over all the disks. So, the striping of the files data and the check data is done over all the disks. So, here there is no single check disk. The parity bits are calculated and they are kept along with the data and is kept in multiple disks. So, this will improve the performance of multiple writes, because you can do multiple writes in parallel. It will also improve the reading. So, here you find in the case of level 4, what we saw, you had a separate disk for storing the parity, but now here what is done is that the parity is stored along with the data in different disks. So, the parity for disk 1 is kept in disk 2, parity for disk 2 is kept in disk 3, etc., and so on. And then they have another RAID level 10, where they try to combine level 0 and level 1, and hence they try to include the striping as well as redundancy. So, by you have striping as well as mirroring and try to combine both, and this is the most high performance system as well as the most expensive system. So, summary. So, in this module we will learn different aspects related to memory management, like formatting of disk, boot blocks, maintaining bad blocks and handling bad blocks, and then we saw how swap space is managed. We also learned different RAID levels. References. Thank you.